Hello everyone and welcome back to another video. In this video, we want to see a showcase of all the codes and classes we have seen so far. We will see different implementations of Index Storage Manager and how I have managed headers so far. Then we see the caching decorators. Also, we will take a look at Hexdump of index files as we create them. And in the end of the video, I have a bonus surprise for you. So I go ahead and create a class called showcase, but I won't add it to the Git. So let's create our first b+3 index. The index tree that we will create will have degree of 4, which means each node can have maximum 3 keys. And we will use compact file index storage manager to store the index. First, we need to create a path to store the database files. So I will create it in the temp directory. Next, we need to configure the database engine. And we should set the degree of the tree here as well. Next, we need to create an instance of compact file index storage manager. The first argument is a string, its custom name for our index. Then we need to pass an index header manager factory, which I will use JSON index header manager factory. And we will see this class as well very soon. Next, we need to pass the engine config. And at last, we need to pass a file handler pool, which for now I will pass unlimited file handler pool. The unlimited file handler pool itself needs file handler factory, and I will use this singleton file handler factory instance. We have seen what this file handler class is before. It will create an asynchronous file channel based on the provided path, but also it can get executor service, which can be passed to the asynchronous file channel, so we can handle how many threads work with the file. The file handler factory is an interface which provides file handler based on the given path, and the main implementation is singleton file handler factory, which you can either create a file handler factory without an executor service. You can pass thread count and it will create an executor service with fixed thread pool, or you can pass the executor service. Going back to our showcase, let's take a quick look at JSON index header manager. It is an implementation of index header manager interface, and if we take a look at that one, I have changed it recently, and in most cases we need to get the root of an index or set the root of an index. And also, if our index supports chunking, you can use these extra methods to find different chunks and where they begin. The JSON implementation of this interface uses JSON library from Google, and it will keep updating a file. And the path of this file is provided by Index Storage Manager. We will soon see the contents of this file, but to represent them as Java classes, we can look at this JHeader class. We have a map of an index to the location of the root, and another map which maps index to the list of locations in different chunks. I also want to mention that when our database gets completed, the end user that uses the library or the database does not have to work with any of these classes that we are working with today. They would only need to config the engine, and the rest of the usage is completely different. But for now, our perspective is from the person who is implementing this database. Now we can start creating an index manager, and we have seen different implementations of it in previous video. If you remember, I have talked about cluster index manager. So we will use cluster b+3 index manager. If you remember, in cluster index manager, we knew that all of the values are of type pointers. So we only need to know the type of the key. For this example, we will use integer as our key type. Next, to construct it, we need to know the degree of the tree, which is 4 in our case. index storage manager, which we have just created in line 38. Then we can pass index IO session factory, which we won't do that, and I have explained why in previous video. Instead, we have to create immutable binary object wrapper for the type integer. We can either support 0 or not. For now, we'll keep supporting zeros. So I will use this class, and we are done. So let's begin by adding an index using our index manager. You can see that we need an index ID, and we use the number 1 for it. Then an integer identifier, which will be used as a key in B+3. We use number 10 for it. And at last, we need a pointer to the data on disk. Well, right now we don't have a data on disk, so we cannot have a pointer to it, but we can just create a fake one. We set the type of our pointer to data. We choose the position 69 and the chunk 0. And we can use this fake pointer in our add index method. Also, let's try getting the same identifier from the same index and compare it with the fake pointer. We use the getIndex method on index 1 with the same identifier. And if we find it, we print what was the expected pointer and what we found. So let's run our showcase. The expected and the found pointers are the same. And it tells us the path of the database is here. We have printed it on 935. Let's update it. So let's take a look at this path and see what we can learn. If I run ls, we can see the files in this directory. And we see 2 files are created. Let's begin by seeing the contents of header.bin. As you can see, the contents is in JSON format. And this section is a map between an index and the position of the root node. So the root node of index 1 is in chunk 0 at offset 0. And the next key, as I've talked before, maps each chunk to the list of indexes, and it shows where each index starts in that chunk. The second file is an index file for chunk 0 of the index called showcase_1. And that is the custom name that we passed to our compact file index storage manager. To see the contents of this file, I use Hexdump. Each row gives us information about 16 bytes of this file. And here we can understand the number of the first byte in the first row. If we go back to the contents of previous videos, where we talked about binary representation of B+3 nodes, we saw that in both leaf and internal node, the first byte is a flag. And that flag byte would show 2 things: if the node is a root and the type of the node. Now, if we take a look at this abstract tree node, which we have discussed in previous video, the leaf node bit flag looks something like this, and the root node bit flag looks something like this. If we do an bitwise OR operation between these 2 flags, we will have something like this. And this equals to the number 6, and its representation in hexadecimal format also looks like 6. So this 06 equals to this one, which means our node is a root node of type leaf. Now, before we continue, I've made a small mistake here. If we go back to our showcase, I said that we don't want to support 0 for now. So we need to make a change to this immutable binary object wrapper. And instead of integer, we use no 0 integer. If I run the code again, the path of the database has changed. So let's go to the new path and let's run a hexdump on the index file again. So now this is the updated hexdump. Back to our blackboard. In binary representation of leaf node, The next 4 bytes would represent the first key in the node. Coming back to our Hexdump, these are the next 4 bytes, and the hexadecimal number of 0A equals to decimal number of 10. Looking back at our code, the index or the identifier that we have added was also number 10. So these 4 bytes represent this number 10. Let us begin with extracting 13 bytes. So this 01 is the first, 12, 13. So let me copy this. So if we go back to pointer definition, a pointer has 1 byte which shows the type of the pointer. Then it has 8 bytes to show the position and 4 bytes to show the chunk, which position is of type long and chunk is of type integer. Now we can see here that the first byte is 1, and that means the type of the pointer is of type data, which equals to the type of our fake pointer. Then we have 70 bytes and then number 45 in hexadecimal, and 45 in hexadecimal equals to the number 69 in decimal. So these 8 bytes are for the position of type long, and then we have 40 bytes, which means the chunk equals to 0, as we see here. As you can see, the rest of the tree is filled with 0 bytes, since we haven't added any more keys. So now let's go ahead and add more keys. We now also have 20 and 30 in our tree. So let's run this code. So this is the hex dump of the new index file. We have seen it till here before. So the next 4 bytes represent the next key in our tree, which is number 20. And then we again have a pointer, which is stored at the highlighted chunk of the hex dump. Again, the type is data because we are storing the same fake pointer, and the position is 45 in hexadecimal. So after that, we have the next key, which is 30, and 1e in hexadecimal equals to 30. Then we again have our pointer in this highlighted section. Now we understand that until this byte, we have our keys and values, but as I have discussed before, we should also have some paddings. This last byte is the 52nd byte of this index file, and to see where the padding ends, we can use the code. If we request for an empty node from index storage manager, it returns us the byte array of the size of the node. So we can print the length of that one and run the code again. As you can see here, and I hope this is not too small for you, the node size is 120. And we understood that the first 52 bytes are used for keys and values. Now we know that a leaf node also has pointers to previous and next nodes. So these pointers reserve 26 bytes. And the sum of these two is 78. So the padding size right now is 42. Now that seems like a pretty large number. And this is because our index storage manager doesn't know the type of the keys and values in our tree. By default, it thinks that the size of the keys are 8 bytes, which equals to the size of a long. However, we can change this in engine config. The cluster index key strategy is used for the same thing, so we can set it to an integer. And if we look at the engine config, we can see that the default was long. Also, we don't use integer for now, we use no zero integer. So let's run this code again. And now we can see that the node size is 96, which if we change our equation here, 96 minus 78 equals to 80. And that is our padding size, and it makes way more sense. Now let's see what happens if we add one more index. Also this time, we want to see the pointer to the index. So I grab the node that has stored the index. Let's run this code. So The new node is stored at position 96, and let's find that in our Hexdump. The hexadecimal value of 96 is 60. So here we have the beginning of our new node. So right now we have two leaf nodes. And the new node is also of type leaf. 1e is the first key that it stores, which is the hexadecimal value of the number 30. We have talked about this before. When the leaf node has no space left to add new key, it will split into two nodes. And this 30 in this case is splitted and moved to the newly created leaf node. Next, we have the pointer type of key 30. Then we have 8 bytes for the pointer position and 4 bytes for the chunk, which is 0. Then we have our next key. So the next 4 bytes are for the key. And the hexadecimal value of 28 is the decimal value of 40, which we have added here. Then we have the pointer, which is the same as before. And then we have 4 bytes for the chunk. Since the degree of the tree is 4, we should have 3 keys, and our last key is empty. So we need 4 bytes for the key and 13 bytes for the pointer. And now the question is, what is this 2 here? So as we know, our first node is in the position 0, and the second one is at 96. We have seen this. And each node should have a pointer to its sibling. We first store the pointer to the previous sibling, and then we store the pointer to the next sibling, which is empty in this case and this case. So this 2 here is the type of the pointer. And if I open the pointer class, 2 is for type node. So it means that this leaf node is pointing to another node, which is this previous one. The next 8 bytes is for the position of the previous node, which is 0. And then the next 4 bytes is for the chunk, which is also 0. Now, if we look at the first node, this is where the second key is over, and here the pointer starts. This is where it ends. And then we have 4 bytes for the third key, which is empty for now. And we should have 13 bytes for the pointer of that empty key, which we don't see it here in the Hexdump. And eventually in the end, we get to a pointer, which again is of type node. It is pointing to the position 60, hexadecimal 60, which the decimal value would be 96. And that is where the second leaf node starts. And the chunk again is 0. We have more data starting down here. It's a node that the flag has the value of 5. If we go back and take a look at the abstract tree node, if we use bitwise OR operation between the root bit and internal node bit, the value would be 5. It will be like this. And actually, if you look back, the previous nodes are no longer roots. They are just leaf nodes. So the value for the flag is only 2. Now remember that a leaf node starts with a pointer. So this 2 that we see here is the type of a pointer which points to a node that stores values smaller than x, or whatever the number is for the first key. Then we have the position of that node, which is 0. So this is pointing to the first leaf node, and then the chunk. Then we have the key, which again it is 1e. So this key is 30. And then we have the next pointer. The type is node. The position is 60 in hexadecimal, which is 96. So this is the second leaf node. And it's in chunk 0. And the rest of the keys and pointers are just empty. So I have shown you before how compact file index storage manager works. It keeps all of the nodes of the same index next to each other, and it keeps track of where does each index begin in different chunks. One of the parameters in our engine config is B3 growth node allocation count. And by setting this number, each time that we want to allocate a space for a new node, instead of only allocating for a single node, we allocate for 10 nodes in this example. To see it in action, I will first set it to 1 and run this code. And you can see that the size of our index file is 288 bytes. Now I will increase it to 100 and run the code again. And you can see the number of bytes for our index file has increased. But so far we have created only 3 nodes. So most of these bytes are just empty. Now let's say I have an index other than 1 and I want to add a key to that one. So we set this to 420, for example. And the identifier we add is 100. The hexadecimal value of 420 is 1A4, and the hexadecimal value of 100 is 64. Now this is the full code, and let's run it. So this is the hex dump of the index file. This is the first leaf node of index 1. This should be the second one. And here you have the internal node or the root of the index 1. Now you can see here that the next node starts at byte 2580, and that equals to 9600 in decimal, which makes sense because the engine is configured to add 100 new nodes when we are allocating a space from the disk, and each node is 96 bytes in our case. And this 64 is the key 100 that we added to this index, which we have done here. Now let's also see the header file. As you can see, we have 2 roots, 1 and 420. And index 1 starts at offset 0 in chunk 0. And index 420 starts at offset 9600 in chunk 0. So how this works is that to find the position for each root node, we have to create the sum of the offset of that index and the offset where that index begins in the chunk of the root node. So we need the sum of these two numbers and the sum of these two numbers. This is because if we allocate a space in the middle of the file, we don't want to update all of the nodes in that file and change the position of each pointer. The next index storage manager that we're gonna see is single file index storage manager. And we cannot pass a custom name to it. Everything else in our code remains the same. So now let's go ahead and see the difference between these two implementations. As you can see, the file name that it creates is index.bin, and that's same for all of the cases. We cannot change it because all of the indexes are stored in the single file. Next, I'm gonna run hexdump on this file. So like before, these 3 nodes are for index 1, and this node is for index 420. But the main difference is that this index or this node is not started at 9600. It is just added to the last node available in this index file. But the size of the file is still 9600. So the allocation has happened and we have an empty space here. To understand these differences in more details, check episode 6 where I have discussed index storage manager. Now let's take a look at the header file as well. As you can see in this implementation, we don't update chunk index offset since all of the nodes are added to the same file next to each other, and we cannot have multiple chunks. The next implementation to take a look at is extended file index storage manager. And this one also accepts a custom name. So let's run the code and see how it works. As you can see, it has created 2 index files, and one of them is for index number 1 and the other one is for index 420. Now what we can do here is to set the engine to only allocate 2 extra nodes per each disk allocation, and also set the maximum index file size. We know that for our example, each index is 96 bytes, so we set the maximum file size like this. Let's run the code again. This time we have 3 chunks for index 1 because we have added 4 keys into it and the maximum file size has exceeded. Also, if we take a look at the header, we can see that this implementation also doesn't track the chunks. However, I think this is a bug that should be fixed and we should not have this content here. As I have said in episode 6, extended file index storage manager and compact file index storage manager support chunking. And as you can see, we now have multiple files. And of course, the number of files depends on the configuration per each developer. But as mentioned in the same episode, this is the reason we use file handler pools. And I have changed the unlimited file handler pool to the limited one, where we can set the maximum files that can be opened in the pool. Now that we have seen all the different implementations of Index Storage Manager, let's also see how caching works. To do that, first I will switch back to Compact File Index Storage Manager. This is not necessary, but it will help my showcase. And as mentioned in previous video, we have a decorator for Index Manager which supports caching. So we will create an instance of that and pass the index manager that we want to decorate and the number of entries that we want to cache, for example 100. I'm gonna comment this for now and come back down here. Let's have an error message for the case where the key is not found in our index manager, and I'm gonna add a breaking point here, and instead of running the program normally, I will use a debugger. So we are in the line where we are looking for the identifier 10 in index 1. And if I check the console, this is the location of the database. As you can see, we have multiple index files here. And again, this is because we have a maximum file size. So I'm gonna go ahead and remove all of these. And we are only left with the header file. Of course, at this point, our database is corrupted and cannot function anymore. And to make sure, I will go back to the debugger and resume the program. So as you can see, the NA or not available is printed here, which means that we could not find key 10 in index 1 because the files were removed. Now let's uncomment this cache and try again. And again, remove all of the index files. Now, if I resume the program, you can see that the output is different from the previous time. We actually found the key that we were looking for. And this doesn't mean that the database is no longer corrupted. It only means that maximum hundreds of these keys may be present in the cache. We are now at the bonus part of this video. You're gonna see something for the first time, which I haven't even done it myself before. And you can consider this as a showcase of how real data would be stored in our database. So again, the example codes that we will write here are like the backbone of a database system. And the end user or the developer that is using the database will not be dealing with these codes. So in real example, we will have a row that we want to add to the database. And of course, before that, we need to define an schema. So basically, the database knows where each column is stored in a single row. But for the sake of example, since I haven't finished the database yet, we assume that this is the structure of a single row in some table. Now, of course, the database has a mechanism to convert this row to a byte array and also convert byte arrays to rows. And this is called the serialization process. For the case of a string, we can do it like this. And our expectation here is to be able to store this serialized row somewhere on the disk and get a pointer to the location where it is stored. In the time of recording this video, I have a class that has implemented this functionality and we will use it here. It is called Database Storage Manager, and we should pass engine config and a file handler pool to this class as well. Now this Database Storage Manager has a method called store, which accepts collection ID, and you can assume that this collection ID equals to an identifier for each table. And for this example, we use collection ID of 1. And the data is the data that we want to store in the database. So it's this serialized row. The output of this method is a pointer, which points to the location where the data is stored. What our database should do next is to create an index for this pointer, and we have an index manager for that. So again, we need an index ID here. In case all of our tables or collections have only a single index, this index ID could be equal to the collection ID. But in other cases, this index ID is more related to the field or the column of the table. But for now, I just keep it as 1. And the identifier that I want to add is 10. Here I said that the PK or the primary key is 10, and the value is this pointer. In this section, we have inserted to our database. So let's also see how selecting item from database would work. We should first go after our index and get the index to the primary key that we are looking for. Now these two pointers should be equal. Therefore, we should be able to ask the database storage manager to grab the data for us at this pointer. If the database storage manager can't find the index, we can print data not found. Otherwise, we can get the optional data. The result is of type DBObjectWrapper. Let's see the methods of this class. We can get the data size. We can activate it, modify the data, set the size, deactivate. We can see if the data is removed or not. And the collection ID where the data belongs to. We will understand the rest of the methods in next videos. So for now, I will just print collection ID. And then I will grab the serialized data from this class. So again, this serialized row and this data should be equal. Therefore, I should be able to deserialize it. And after that, I just print the deserialized row. So let's see if this works. And it did. You can see that this deserialized data is returned from the database, and the value equals to what we have serialized and stored in the database. But also let's take a look at this directory. We have 3 files. One of them is header, which is used by the index. We have the index file, and we also have the binary file for the database, which again supports chunking, and this is the chunk 0.